Jai Hind, viewers. We welcome you back to another episode from MRO Digest forums. Today, we are talking about the challenges, the evolution in battery technology from lithium ion and then towards the future. It's a very important topic which is having a very wide ranging impact today. And we have with us Brigadier YVR Vijay to talk about it. He's an expert in the field. He has a very illustrious career both in the army as the corporate sector, and he has studied this topic and he has a reputation. He comes as an expert speaker in many forums. And today I will start with asking him the first question. That is, despite rapid growth in lithium ion battery technology, there are a number of challenges which are being faced. So I request him to elaborate on them. Brigadier Vijay, please.
Jayan sir, Jayan to viewers also. So this is a very important question because today, as the world is switching over to electric vehicles, we are finding a huge interest in renewable energy and in renewable energy, hybrid renewable energy systems where we have a mix of wind, solar and storage. We are finding that the world is very heavily oriented today to lithium ion technology, lithium ion batteries. But while lithium ion batteries have excellent energy density, they are comparatively lightweight compared to the olden day batteries, there are still certain issues which are there with lithium ion, and hence almost all the major universities across the world are being heavily funded by industry to do more research into energy storage. And so battery technology is developing rapidly. So if we see the issues with lithium ion battery, which is using basically nowadays on the anode side, you have the lithium, you have liquid electrolytes. There are a number of issues which are coming up. They are widely used, of course, because they got good energy density, relatively lightweight. They have the ability to be recharged. But there are areas where improvement is still required. The first is, as you keep charging and recharging a lithium ion battery, its performance degradation starts taking place. The capability of it to hold charge, the capability of it to get charged to the full level, and its discharge when not being used. Then it has received a lot of adverse media due to overheating problems. Overheating, which has resulted often in fires, which look very dramatic when seen on TV and on screen, because it's very difficult to switch off a fire caused due to lithium ion batteries. There's a problem of overcharging. As you overcharge lithium ion battery, it tends to degrade faster. So there's always your battery management systems have to be such that control the level you charge it up to, and also you don't let it fall to zero. Now, lithium is a rare material. It's not found anywhere in the world so easily. And there are a few mines in Africa, in South America, some found in India. And these are largely dominated by the Chinese. And hence, as a source, lithium becomes very costly because there are controls over this. And the total amount of lithium is quite less. So the world is looking at a lot of areas of how we can use commonly used metals instead of lithium to produce batteries. Then there's an environmental impact due to, you cannot dispose these sort of batteries easily. They have their own environmental hazards. So that is another area where work is going on. Today, average battery per kilowatt hour weighs something like 10 to 15 kgs. So in a EV, where you need about 50 kilowatt hour batteries, it adds a ton of weight to the car. And while if you use lead acid, it might add 4 or 5 tons, but you want to go lighter. The lighter the battery, the better it is for the car. There are lesser mechanical issues. and you can pack in more battery onto the same car. So there's a lot of work required to find materials which give better energy density than lithium-ion battery. Safety risks, I already discussed. There are chances of fire, there are chances of overheating. So this is one area where a lot of work is going on. It has been noticed that the life cycle of a lithium-ion battery, once it has done about 3,000-4,000 cycles of charging and discharging, goes down. Its performance goes down. So there's a limited life cycle in case of batteries. And as we try to get the cost of EVs down, we want to increase the life of batteries. Otherwise, every 4-5 years, if you have changed the battery of a EV, then the cost of EVs becomes difficult. It becomes tough for them to compete with the normal IC engine vehicles. Another area where EVs are struggling today is performance in extreme temperatures. Temperatures where the cold temperatures going below 50 degrees Fahrenheit or above 50 degrees centigrade. In these sort of places, the performance of a lithium-ion battery is greatly impaired. So these are the issues being faced by lithium-ion batteries, on which the world is doing research. All the technical educational institutions are doing a lot of research.
So thank you for that, Brigadier Vijay. So from what you have said, what comes to mind is that in the case of electrical vehicles and renewable energy, how are the batteries likely to evolve in the, say, the next 2 decades? Brigadier Vijay, please.
Yes. So there are a lot of key trends. As I said, a lot of research is going on. There are a lot of key trends which are shaping the future of batteries required for electric vehicles and for the energy grids, and also for the electronics industry. So there are a lot of advances in the lithium-ion batteries. We are looking at alternatives to lithium-ion batteries. We are looking for sudden burst of energy, short-term response energy storage devices, improved battery energy storage systems, improved thermal energy storage systems. There's a lot of work going on in reduced oxidation flow batteries. We are also looking in view of the large number of EVs to look at distributed storage, because imagine if 1 million EVs are running in a city, then you've got so much distributed storage of charge available, of electricity available. We are looking at solid state batteries. There's a lot of research going into hydrogen storage. And in fact, energy storage is now being thought of as a service. Like you have software as a service, your energy storage is coming as a service. So the areas where we are looking and expecting a lot of development is first on improved energy density. As I said today, a kilowatt hour of lithium-ion battery is around 10 kgs, 15 kgs almost. We are looking at much better energy density, so that for a kg of actual physical weight, we can store maybe 2 kilowatt or 3 kilowatts. The major cost component in EVs today, on which is driving up a renewable energy hybrid product, is the cost of lithium-ion battery. Almost 30-40% of the entire cost of an EV is due to the battery cost. So we're looking at alternatives to reduce the cost of these batteries. We're looking at batteries which are more environmentally friendly, so which recycle more easily, can be reused or are not so harmful to the environment. We are looking at solid state batteries, which I will cover in detail, which are much more safer, where we are replacing the liquid electrolyte with a solid electrolyte. We are diversifying the number of types of batteries using various types of commonly available metals. We are looking at new technologies in hydrogen batteries, that is the fuel cells. We are looking at keeping the electrolyte away from the main battery and the electrolyte to be flexible in nature. We are looking at fast charging. Today, one of the major issues EVs face is the time to charge to full strength. Nobody likes on a long drive to keep his car parked for a couple of hours or maybe more, just charging up. When he can actually, when he compared to an IC engine, in a minute he can fill up his fuel tank. So we're looking at faster charging systems. We are looking at how do we reduce the charging time of a EV battery to a few minutes or even a minute. And finally, improvements in the battery management system so that there is more accurate analytics available to the driver and the user on the health of his systems. So these are the areas where we expect a number of key trends and developments which are shaping the future of battery technologies.
Thank you for that, Brig Vijay. So now EVs have got some challenges, and so what one then thinks of is that what are the top alternatives to lithium-ion battery technology where research is going on? Brig Vijay, please.
Yes. So there is a number of areas where research is going on. So I will cover 10 of the alternatives which are coming up. And basically, the world is looking for a greener, better lithium battery, first of all. We want recharge efficiencies to improve. We do not want to use costly, rare elements like cobalt, lithium by itself. So we are looking at nickel, manganese, phosphorus, cobalt also, but with reduced numbers. So the first of the alternatives which I will cover are the lithium ion phosphate battery. There are big companies in the world, in China and US. In fact, in battery technology, China is leading the world. A huge amount of research is going into this field. Most of the alternatives you are finding coming out of China. In fact, more than what are coming out of the US. Now, the lithium ion battery is a type, lithium ion phosphate battery is a type of lithium ion battery, but it's slightly different chemical composition. Now, its advantages are it's much safer, high temperature performance is better. It enables many more, almost 6,000 recycling of charge-discharge cycles. At full charge, its tolerance is better. Its performance degradation at full charge is not like a lithium ion battery. It's far better. And the most important is the energy required to produce a kilowatt hour of lithium ion phosphate battery is much less than a lithium ion battery. So that was the first of the alternatives, the lithium ion phosphate battery. The next area is where we are looking at solid state lithium metal batteries. Now, one of the weaknesses in the traditional lithium ion battery is it does not have a solid electrode. And that creates problems of leakage, it creates problems of fire. A solid state lithium metal battery reduces these. So I've shown you in a diagram how the cathode and the separators are all, it's all solid. Now they use solid electrolytes instead of liquid or gel, which is found in traditional lithium ion. And they offer better energy density, better safety, and potentially much faster charging speeds, which these two graphs will show. So if you see the energy density versus the size, lithium ion is somewhere middle of this chart on the left. Whereas the solid state batteries are more to the right. So they have more energy density for the same weight and volume. And as far as charging speeds go, the fast charging speeds of a solid state battery is much more advanced, by almost 30 to 40% above the normal batteries. Already a lot of solid state batteries are there in the market. Samsung, Sabrent, Intel, Seagate, Micron, SK Hynix, Corsair, Microcenter. These are the ones in the US. There are a number of Chinese brands as well, which are there in the market. The next is, as I brought out, we are looking at how to get cheaper materials. And sodium is very commonly found. So the largest EV company in China, BYD, has recently entered a joint venture with Huawei, and it's creating the world's largest sodium-ion battery factory for small electric vehicles. Because sodium is so much cheaper, it's available in mass easily available, and even though it may be heavier than lithium, but when we come to the energy grid, there I'm not worried about weight. So sodium ion batteries use sodium ions instead of lithium ions as the charge carrier. So they're a great alternative for large-scale energy storage. So on the grid, I would rather use a sodium-ion battery than a lithium-ion battery, because while it may be heavier, weight has no meaning in a static storage. But it is much, much cheaper. So it's cheaper. I can put in huge capacities, a megawatt hour or 10 megawatt hour type of storage capacity using sodium, and the cost saving compared to lithium ion will be immense. Next, similarly, like sodium, you have the Zinc Air battery. There are major zinc companies which I have listed here on this who are already manufacturing commercially. Zinc is used instead of lithium. Air is the cathode in between. So the Zinc Air battery uses oxygen as a reactant, which makes them much lighter. So therefore, the energy density goes up. So then it becomes useful for electric vehicles. Because zinc is easily available and cheaper compared to lithium, it is suitable for even the grid energy storage. One of the problems being faced and work going on is it discharges quickly, almost like a lead acid battery. And its recharging efficiency is poor. So it fails in a lesser number of cycles. But as I said, these are areas of research. Zinc Air batteries, Zinc Air fuel cells are powered by oxidizing zinc with oxygen from the air. They're used now in electronics in the form of button cells. They're used in cameras and, of course, in EVs. Another very interesting is the flow battery. A flow battery is where you have flexibility with the positioning of the electrolyte tanks. So VRB Energy is, as an example I'm giving here, the world's longest lasting vanadium flow batteries. Then you have a number of Chinese companies, Rongke, Corid. Now, how does a flow battery work? It's a rechargeable battery in which the electrolyte flows through one or more electrochemical cells from one or more tanks. So you have flexibility there. You can have one tank, two tanks, three tanks. With a simple flow battery, it is possible to increase the energy storage capacity by just increasing the number of these tanks or the size of the tank so that you can put more electrolyte. These can be connected in series, in parallel, so you can determine how the power flows. And, this sort of structure makes it much more flexible. When you have separated out the electrolyte from the main battery. Another alternative is the use of graphene. And a lot of work is being done, especially for the electronics industry in graphene battery systems. Samsung, Huawei, Cabot, all working on this. Now, graphene is a one-atom thick layer of carbon. So it's very fine. It has excellent conductivity properties, for almost close to superconductor levels. And a graphene-based battery offers high energy density, rapid charging capabilities, improved lifespan. This is almost state-of-the-art work going on. I don't see them coming out properly commercially for maybe 10 years. But they offer superb capacity, charging speeds, the energy density is very high, lifespan is more, it is very safe and stable. There's a lot of research going on, but once these are properly addressed, it will transform the energy storage sector. A lot of the problems of heavy batteries, bulky batteries will be sorted out in graphene batteries. Next is, like we discussed, the zinc and aluminum and sodium air battery. You can use aluminum instead of zinc. So you have the aluminum air batteries. Mostly Chinese companies are working on this. Aluminum, as you know, is very light. So the energy density of the aluminum air battery is good. And you can extract and reuse the aluminum as well. So here aluminum ions are used as charge carriers. They give you the potential for high energy density, low cost. Some of the big advantages is it's non-polluting, lightweight, high energy density. Performance characteristics are not yet comparable to a sodium lithium ion battery. So work and research is going on how to improve their performance, how to improve their cycle life. But aluminum ion batteries, because of the easy availability of aluminum, makes it cheaper, lighter. So there are great advantages. Like you have the aluminum air battery and the sodium ion battery, you have the magnesium, where magnesium is the anode instead of lithium. So they use magnesium ions instead of lithium ions. Again, much higher energy density than lithium ion, and magnesium is abundantly available. So low cost, lightweight, it is friendly to the environment, but magnesium corrodes faster, as we all know, and it reacts with the electrolyte. So there are problems, and this is one area where research is going on as to how to put separators between the electrolyte and the anode so that the corrosion is reduced. Now we come to a very interesting totally different from a lithium ion technology, is the super use of superconductors for magnetic energy storage. So SMES, super magnetic energy storage systems, store energy in a magnetic field created by the flow of direct current, which has been cryogenically cooled. You know, a superconductor, once it goes below a certain temperature, its resistivity falls to almost zero. And that's when it becomes a true superconductor. And a typical system will consist of the coil, the superconducting coil, the power conditioning system, and a cryogenic cooling system. Once this coil is charged, the current will not decay. Magnetic energy can be stored indefinitely. Most important advantage of this is the time delay. Charging times are very short. Discharging times can be controlled, and it can be sped up, controlled. Power is available almost instantaneously. Very high power output can be provided for brief times. If the demand is immediate, SMES is an excellent system. The loss of power is negligible compared to other storage methods, because the electric currents encounter almost no resistance. So there's no heating. Additionally, there is no movement, so it's motionless. It is highly reliable. There is again a lot of research going into this. There are large manufacturers who are coming in this more for the grid. So you have a number of companies in USA, in Japan, in China who are working on this. Then we come, of course, to the most commonly used hydrogen systems, where you have the hydrogen fuel cell. Basically, hydrogen is fed at the anode, oxygen at the cathode, and when it reacts and forms water, the electricity is produced, and the discharge is water. It's the cleanest form of energy. I've shown a photograph of the Toyota Mira car, which is one of the most popular hydrogen cars today using the fuel cell. So you have hydrogen tanks, you take in air, you have the fuel cell system, you have extra batteries for extra power, and the electric motor. And today we know about 5 kilos hydrogen fuel tanks on a Mira gives almost 650 kilometers of range, and it is fast improving. So fuel cells basically convert the chemical energy of hydrogen or methanol into electricity. Methanol is CH4, into electricity through an electrochemical process. They give good energy efficiency, as I just explained in the Mira, and they can be used as an alternative to batteries in many applications. Basically, hydrogen is the lightest element. So for the shipping industry, later on for the aircraft industry, for the steel industry, as well as for the concrete industry, you will find renewable energy coming in through hydrogen. It is much more lighter. You can have huge spaces. And if you want a ship, if you want to have, say, a megawatt hour of storage, if you go in for lithium ion, it will be immensely heavy. But if you go in for hydrogen-based system, it will be much lighter. Same with large trucking industry, the steel industry, the concrete industry. So in conclusion, what I would say, since I covered the top 10 alternative battery technology trends as of today, that all these alternatives are showing promise. R&D is going on. They're at various stages of development. There is some commercialization taking place. Based on your specific applications, do you want it for EVs? Do you want it for energy storage? Do you want it for the shipping industry? Do you want it for the regular industry like the steel and concrete? The type of battery will change and depends on applications, cost, safety requirements, and availability of resources. So with that, I have concluded my talk on alternatives to the lithium ion and developments which are taking place in battery technology. Thank you.
Thank you very much, Brigadier Vijay, for sharing your depth and the breadth of knowledge on this very important topic in such detail with us. And we thank you, viewers, for being with us. And the link to Brigadier Vijay's LinkedIn profile are there in the show notes below. You're welcome to get in touch with him for any further information. With that, we come to the end of this particular episode, and we look forward to bringing more such episode to you in the future. Jai Hind.